Hey guys, today we're going to do a lesson on indirect measurement. An indirect measurement is used when it would otherwise be difficult to measure the height or the length of something. And what we'll do is we'll use similar triangles in order to find that length or that height. So let's look at example one. It says a fire hydrant 2.5 feet high casts a 5-foot shadow. How tall is a street light that casts a 26-foot shadow at the same time? Let H represent the height of the street light. As you can see, the diagram's already drawn for us. So I'm going to go ahead and just complete our triangles. It's a right triangle right there so that we can set up our proportion. Okay, so right now there's many different ways, obviously using properties of proportions that I could set this up. So I'll use height of the street lamp to height of the fire hydrant as shadow of the street lamp is to shadow of the fire hydrant. So if I were to solve that proportion, I would get the height of the street lamp as 13 feet high. Okay. All right, let's look at example two where the diagram is not drawn for us. All right, so at a certain time of day, a 6-foot man casts a 4-foot shadow. Okay, so go down a little bit. All right, so let's draw our 6-foot man. All right, and there's the shadow. So the shadow is 4 feet, he's 6 feet. At the same time of day, how tall is a tree that casts an 18-foot shadow? So draw a little tree. There's the tree shadow. We want to know the height of the tree or how tall is the tree. So again, these are right triangles, if you will, and we will set up a proportion in order to find the tree's height. All right, so, and again, you can set this up many different correct ways. Somehow I did not write in the shadow of the man. Okay, so x over 18 equals over 4. So if I were to solve this, I would get the height of the tree to be 27 feet. Okay, so now let's look at the third example. In the figure at the right, triangle DBA is similar to triangle ECA. Ramon wants to know the distance across the lake. So again, finding the distance across the lake would be very, very difficult unless you were using indirect measurement. All right, so again, I have similar triangles. One is nested inside of the other. Okay, so I'm going to go ahead and set up a proportion. 320 over 482, and 482 is this entire length, 482 meters, okay, is equal to 40 over D, which is the distance across the lake. So if I were to solve that proportion, I would get the distance to be, oh, somehow this is okay. I would get the distance to be 60.25 meters, or 60.25 meters. Okay. Somehow not wanting to write today. Okay, now obviously you can use properties of proportions and you can set this up differently and still get the same correct answer. So one other way, we'll just do one other way, there's multiple other ways to set this up, is you can say 320 over 40 to 482 over D. And again, if you used other properties of proportions, there are other correct ways to set it up. And you would still get D equals 60.25 meters. Okay, so now looking at example 4, again, we know that triangles are similar if their corresponding angles are congruent and corresponding sides are in proportion. Okay, so we know that these two angles right here are vertical angles, so they're congruent. And you also see that these two lines are parallel, so obviously alternate interior angles would be congruent. Okay, same thing with these two. Okay, so now we're going to set up a proportion to again find how wide the lake is. Okay, so again, multiple ways to set up your proportions. As long as you're using properties of proportions and you're staying consistent with your corresponding sides, you will get the same correct answer. And we'll call this distance across the lake, or the width of the lake, X. And that's kind of, I know that's a little redundant because this point right here is also called X, so just be careful with that. If you're more comfortable, maybe pick R or Q or something like that. That doesn't represent a point. or vertex of one of the triangles. All right, so 6 over x equals 8 over 104. Okay, so, and if you want to, again, as I mentioned last week, you can always redraw one of the triangles to be oriented the same way so that you can see the corresponding sides a little bit better if that helps you, but not necessary. So when we solve this for x, we get x equals 78 meters. So the width of that lake is 78 meters. Okay, let's continue on. And I'm going to let you guys actually go ahead and try example 5. I'm going to get the diagram set up because this is going to be another one where the triangle's nested inside of, or the smaller triangle, I should say, is nested inside of the larger triangle. And I want to make sure you're comfortable with that wording where it says the end of the building shadow coincides with the end of Kevin's shadow. So I'll go ahead and get you started on the diagram, and then you guys can solve this. So the sun is, maybe I should read it. The sun is shining down on Philly today. Kevin, who is 6 feet tall, so let's go ahead and draw Kevin, stands 21 feet from a building. So here's my building, okay? And he's, obviously this diagram is not going to be drawn to scale, so excuse my artwork here. Okay, so the building is 62 feet tall, so let's go ahead and label that, okay? The end of the building shadow, again, coincides with the end of Kevin's shadow. So here's Kevin's shadow. All right, so then to complete my triangle, and again, not the best triangle in the world. Okay, find the length of his shadow. So essentially, we want to get this distance right here, which we'll call x. Okay, so I'm going to go ahead and set up my proportion. Oh, I forgot to put in the height of Kevin, and he is 6 feet. Notice all my units match, so that makes it nice and easy. As we get further down in these problems, you're going to see that we may have to do some converting. Okay. And remember, this entire length right here is x plus 21. Okay. So we have to remember to do that. So when you're setting up your proportion, or the proportion is set up, but when you're going to solve this, remember you're going to have to distribute your 6 through the x plus 21. So I'll let you guys go ahead and finish that or work on that, and then we'll be right back. Okay, so once you solve that proportion, you should have gotten that shadow of Kevin to be 2.25 feet. Okay, so let's continue on. All right, so let's look at example 6 here. So example 6, Lisa, who is 5 feet 9 inches tall, casts a shadow that is 10 feet 6 inches long. The end of her shadow coincides with the end of a shadow cast by a building that is 150 feet from Lisa. Find the height of the building. Okay, so we're going to find the height of the building. All right, so let's draw ourselves a little diagram here. So we know Lisa is 5 feet 9 inches tall. Now we're going to have to do some converting. Let's convert into feet, since it looks like when they give us the shadow of the building, that's in feet. So let's go ahead and convert that. So we want to convert that 9 inches into feet. All right, so over here, I'll just do a little bit of side work to do my conversion. Somehow my pen is not writing very well. I don't know why it's doing it. All right. All right, there it is. 9 inches. And I know that there's 12 inches and 1 foot. And I want to go from inches to feet. So essentially, I'm doing 9 divided by 12. And when I do that, I get 0.75 feet. So essentially, Lisa is 5.75 feet. Okay. And that's going to be her height. So 5 is Lisa's height. Okay. Now we're talking about a building. I'm going to kind of squeeze this building in. So again, use my artwork here. Okay. So we want to know essentially, that goes back. We want to know the height of the building. Okay. And it says Lisa's shadow is 10 feet 6 inches long. Okay. So we all know that that's 10.5 if we can that 10.5. Okay. All right, what else can we label? So we also know that the building is 150 feet from Lisa. So I'm going to go ahead and put that in. 150 feet from Lisa, we know distance is 10.5. Okay, so it looks like I have my diagram labeled. And so now, after I did all my converting, I can go ahead and set up my proportion. All right, so I want to know the height of that building. And this time I'll do x over 5.75. Then I've got to do the bottom of that big triangle. So if I add up 150 plus 10.5, my pen is crazy, I get 160.5. 10.5. So when I solve that proportion, should get 87.9 feet. Okay, so I'm going to go ahead and give you guys a chance to work out example 7 and example 8, and then we'll go over that in just a moment. Okay, so for number 7, as you can see, I drew my diagram, labeled it, set up my proportion, and solved. And I was able to find the length of Sean's shadow to be 0.93 feet. Okay, now I'd like you to try number 8. Okay, so now number 8 should be complete, and the tree should be approximately 80.14 feet. Okay, so we have one more problem to do. I'd like you to try number 9, and then we will discuss it. Okay, so now you can see the diagram and the work for example 9. So Curtis is 378 feet from the tree. Hopefully the screencast was helpful, and we will do some guided practice in class or during digital class. Thank you.